Dear students, this is the first lecture. Uh, we'll study electronic devices and circuits EDC. In the first lecture, we'll study about conductors, insulators, semiconductors, and PN junction, and about some devices. Conductors, as you know, have large number of free electrons. Insulators have small number of electrons. Semiconductors have free electrons in between conductors and semiconductors. The most famous semiconductor material is silicon. A silicon has four uh, four valence electrons in its outermost shell. Four valence electrons in outermost shell. It makes covalent bonds with, and each silicon atom makes covalent bonds with four neighboring silicon atoms. So there are, as it seems, there is no free electron, but there are free electrons because they are thermally generated. Because electrons are thermally generated due to the reason that the room temperature is high compared to minus 273 degrees centigrade, 0 Kelvin temperature. That is why we have a number of electrons due to breaking of these bonds, because some bonds are broken due to temperature, due to temperature. That is why we have some free electrons in semiconductors. Right. So in order to increase the conductivity of electrons, or conductivity of semiconductor materials, and turning them into P and N type materials, we dope them. Doping can be of two types. It can either be N type with pentavalent impurity, for example antimony, Sb, and Sb has 5 electrons in its outermost shell. Antimony has 5 electrons, and when we add this as an impurity in silicon, it makes bond with 4 neighboring silicon atoms with 1 free electron, and hence we have a number of free electrons equal to the number of antimony atoms added. Okay, so in a similar way, a material can be p-type, and it can be made p-type by adding a boron atom in the middle. A boron atom has 3 electrons in its outermost shell, so it makes bonds with 3 neighboring silicon atoms, and we have one vacancy for an electron that we call a hole. So a p-type material has holes equal to the number of boron atoms added. So a p-n junction is a combination of the two, the p-type material as well as the n-type material. If we fabricate them in such a way that one side is p and the other side is n, we have these are ions. The ones in the circles are ions. Ions are atoms. Positive ions are atoms who have given away one electron, and negative ions are atoms that have acquired one electron. So in p-type material we have antimony ions in p-type material we have boron ions who have taken one electron in the hole that was created due to adding boron atom, and in an n-type material we have positive antimony ions who have given one electron. So as a result we have large number of electrons in n-type material and large number of holes in a p-type material, and they are called majority carriers. We have majority carriers as holes. We have majority carrier holes in n-type material and majority carrier electrons in p-type material. So when we forward bias a p-n junction, this means we apply a positive voltage to p-type material, p side, and a negative voltage to N side. So as we know that the negative side of this voltage source is able to supply a large number of electrons. So a large number of electrons are pumped into the n-type side, and they have an energy to cross this level, this depletion layer. This layer is called depletion layer. So they have enough energy to cross this depletion layer, and a current is set up. That is we called forward bias PN junction. We have studied many times before in FSC and in the previous course applied physics, I guess. And a reverse bias PN junction is the one where we have applied a positive voltage to the N side and negative voltage to the P side, and as a result the depletion layer, the width of the depletion layer is increased, and we have very small number of electrons passing, and we have very small number of current flowing. We have only the leakage current in this case. Right, let's come to the next slide. A PN junction is also called a diode, where we have an anode and a cathode, and the symbol is like this. You already know this. Okay, so transistors, let's come to the transistors. The course is mainly about transistors, and that was only some background. Transistors, they can either be, we will study two types of transistors in this course: BJTs, bipolar junction transistors, and FETs, field effect transistors. A BJT, bipolar junction transistor, can be of two types. Either it can be an NPN, n-type material, a p-type material, an n-type material, or a PNP. We'll study what an NPN transistor is and how it works. The operation of BJT was studied by us previously, at least in one course. We have three terminals named as emitter, base, and collector. Emitter is heavily doped. This means it has large number of majority carriers, since this is an n-type material. So the majority carriers have to be electrons. The middle region is p-type. It's called based. It's not heavily doped, but it has majority carriers, positive holes. And the collector region, it is also n-type, but it's not that heavily doped as emitter. So if we apply voltage VBE between the base and the emitter, such that base is positive, the positive is connected to the base and negative is connected to the emitter. So this PN junction, this one, base emitter junction, becomes forward bias, because we have applied positive voltage to the P side and negative voltage to the N side. But this junction, it has two junctions. The other junction is base collector junction. This base collector junction, where I have shown these green ions, this junction is reverse biased, because we have applied positive of the battery to the N side, and negative of the battery is effectively to the P side. So therefore this base collector junction is reverse biased. So when we apply this VCE, the voltage between collector and emitter, and VBE has to be equal to the threshold voltage, which is mainly 0.7 for silicon. So if it is at least 0.7 volts, these electrons will have enough energy to cross this reverse bias junction and will meet this positive terminal of the VCE. So this is how a current is set up between emitter and collector. So since we talk about conventional currents, we always take it as from collector to emitter. So since electrons are moving from emitter to collector, only when we have this VBE at least 0.7 volts for silicon. So this is how BJT operates. A BJT, we'll study more in next lectures about BJTs. These are of NPN and PNP types. Here are the symbols. An NPN BJT has base collector emitter, and the sign of the emitter is such that the sign of this arrow is coming out of this vertical base connection, and here the arrow is inward. So that is the primary difference between NP and NPNP transistors. So B stands for base, E stands for emitter, C stands for collector. In the lectures to come, we will talk about the DC biasing of BJT transistors. But before BJT biasing, we'll talk about their input and output characteristics, because we have an input side in most of the cases. For we have input side, which can be either base, collector, or an emitter, or an output side, and we'll draw some characteristics, and then we'll talk about DC biasing and then amplifiers. Thank you very much.